through the title of the presentation today. We will try to give like a quick introduction about acid stimulation. And usually I would like to start with a definition. What does acid stimulation mean? By definition, acid stimulation means it's a process that's unsteady state, non-isothermal, 3D flow in porous media with a chemical reaction need to dissolve the rock. So unsteady state flow. So we are injecting and the velocity and the pressure actually changing with time. They are not constant with time. As you are injecting, both are changing in each minute as you keep injecting your acid. Non-isothermal, as the acid reacts with the formation, it actually sometimes produces temperature. So we may have temperature increase during the reaction. 3D flow, we're not anymore linear flow, we're not anymore radial flow, we're actually much closer to a spherical flow, where the acid, depending on the ratio between the vertical to horizontal permeability, will flow in all the direction. And the most important, we are injecting the acid inside the formation, so we will have a porous medium flow. So we are governed by Darcy law. And as I'm talking about acidizing, we are talking about chemical reactions. So the acid will actually dissolve the rock, and that will result in variation in porosity and permeability. The acid reacts with the rock, and you will have dissolving some rock. So we're expecting increase in the porosity. That will lead to increase in the permeability. However, as any reaction happening, you will have also a reaction product. And the reaction product sometimes will be completely soluble, and then other reactions will not be soluble. So you'll have some precipitation of the reaction product. This will also reduce the porosity and will affect the permeability. So we all the time during the acidizing will have both increase the porosity and permeability, and at the same time reducing the porosity and the permeability. Hopefully at the end of the job, we would like to be sure that we dissolve much more than what we precipitate, leading to a much higher permeability and much higher production. And that's will, at the end, our aims from any acidizing as enhancing well productivity. We would like to be sure that the well will produce on a much better rates comparing before the acidizing. Second, if we have any scale, we need to completely solubilize and dissolve this scale. The third, the skin factor, which is a more important for us. We would like to reduce the skin factor, especially in the near well bore area that coming from the damage. So this is like a quick definition of the acid stimulation. And a question is also like, as a young engineer, when you go to a company, like your manager will come to you and ask, if we have a well, when we will consider an acid treatment, at what condition that you will start thinking that I need an acid treatment for my well? We have only one answer for this question. You use acid treatment when you have damage. We do not use acid treatment just to increase the production. Acid is helped to increase the production if you have a damage. But if you do not have a damage, acid will not actually give you that much improvement of production, except if you are doing something else other than the acid part. But acidizing is always used when you have a damage. And the way that you know that you have a damage is just simple definition. You have unusual or unexpected reduction in oil production. This is can happening like as a gradual. You can see slightly you are losing your production, not the way that the reservoir engineer expecting or the model that can give you, and that can give you evidence that you are building scale with time. So you have a slow reduction in the oil production, or you have suddenly lose your production. Something happened like pretty quickly. And that's happening when you block something. You block the perforation or block part of the tubing. That can happen that you lose the production suddenly. And one of the most important evidence, you are looking to the gas oil ratio or the water cut. If you start seeing unexpected increase in the gas oil ratio or the water cut, that's all can give you evidence that you have some sort of damage. And when you have a damage, at that time you start to thinking that I need an acid to remove this damage. Okay, what type of acidizing stimulation we have? We define the type of acidizing stimulation into two parts. The first, or two types. The first type is called matrix acidizing, and the second one called fractional acidizing. And the distinguish is pretty simple. When we are talking about matrix acidizing, so in this case, we are bumping the acid at a pressure and injection rate less than fracture pressure. So in our case, we are pumping the acid inside the matrix without any intention of breaking this formation or creating a frag. Just pressure and rate low enough to just push the acid through the porous media. And what will be happen, the acid will react with the pores and the natural fracture that exists. However, it will not create additional frag. It just will dissolve the pores and improve your porosity and permeability. And for matrix acidizing, we have a two type of treatment. One for sandstone, depending on the formation type, one called sandstone acidizing, and the other called carbonate acidizing. However, the other type of acid stimulation is called the fracture acidizing, and I believe you can guess right now. In this treatment, we are bumping at a higher pressure than the fracture pressure. We are actually breaking down the formation and create an hydraulic frag, and bumping the acid that will actually stimulate this hydraulic frag and dissolve the created frag surface. We call it etching the created frag surface, and this etching will create uneven fracture safe, so fracture face. And as it closed, you can see the conductivity of the frag is significantly higher. I will have a picture later and we can show you how this is helping. So what type of acid we usually use in acid stimulation treatment? We have a lot of acid that we use. We can define them into different categories. The first category is an inorganic acid. And inorganic acid, we have two main types of acid. We have hydrochloric acid, we call it HCl, and hydrofluoric acid and HF. Just to highlight, HCl is the one that is mainly used, like majority of acidizing somehow contain the HCl. It has the capability of dissolving a lot of mineral, carbonate, oxidized, and a lot of things. The other type is the HF, and the HF acid is the only acid that dissolves sandstone formation. Therefore, when we are talking about sandstone formation, your mind must recover that some sort of HF acid will be present in this formulation. Then we have organic acid, we have acetic, formic, and citric. And we use organic acid in the area that we will not be able to use the inorganic acid, and mainly because of the low corrosion rate. Then we have blends. And as engineers, we really like blends. We try to blend different acids to get a benefit of each one. So we have organic blend like HCl, HF. We have a pure organic blend like acetic formic, or acetic formic citric, or citric acetic. And we also have a blend between organic and inorganic, like formic HCl, or formic HF, or citric HF. So we do blend with all the acid, and in each blend, we try to get the benefits of both. Then, lastly, we have what we call the special acids, and we typically use this acid in a certain condition. Like we have acid like aminocarboxylic acid and GLD, and typically we use this acid when the temperature is extremely high, where like almost 350 and above, like 350 Fahrenheit or 400 Fahrenheit. In this case, the regular acid HCl, HF is a little bit hard to use them. Corrosion rate will be high. So we are looking for some of the special acid at a special condition. Or when we can, HCl is for a certain regulation is not acceptable, so we can use MSA as alternate to the HCl. Any questions so far? Okay, so.
No, you can go ahead, and if there's any question, I will stop you and ask.
Okay, perfect. Okay, so let's go one by one in the acid and let's learn about it. So the first acid I would like to cover the HCl acid system. It is one of the most used acid in acidizing treatment. We use it because it has a lot of good advantage. First, concentration. We can use it between 3 to 28%. So it is a very wide concentration we can use. So we can use it at really diluted condition or really concentrated condition. And the most important part is dissolving power. HCl is the really high dissolving power. It actually, like 1,000 gallon of 15% HCl can dissolve 1,700 pounds of formation, of carbonate formation. So you can dissolve a lot of downhole. You can increase significantly the porosity and significantly the permeability by having this acid. Dissolving power is really huge. And is it cheap? Believe or not, it just costs 70 cents, I will say $0.7 a gallon. So it's a pretty cheap. So cost for us is pretty cheap. So having the highest dissolving power and cost is pretty cheap. So that's a lot of advantage of these acids. Therefore, it's one of the acids that we typically use in the oil and gas industry. And most important part, the reaction product. When it reacts with the formation, whatever came out as the reaction product is completely water soluble. So we do not see a lot of damage due to the reaction product coming from HCl. And I have here the reaction for two formations. The first equation, when HCl reacts with the calcium carbonate, which is the carbonate formation, you can see the reaction product is calcium chloride, which is that salt, CO2, and water. Calcium chloride is a salt and known with high dissolving power, so it's completely soluble in water. So we don't have any precipitation issue when we are using calcium chloride. Even when the HCl reacts with the calcium magnesium carbonate, which is a dolomite formation, still we are getting calcium chloride, magnesium chloride, CO2, and H2O. Everything is soluble in water. So we do not see any precipitation or any concern from precipitation. With the high dissolving power, with no afraid of precipitation, make this acid one of the most used acid system inside the oil and gas industry. Before I go to the concern part, I may like to have a question here. Usually when we talk about acid, we talk about the pH of the fluid will be almost 0. So a quick question for the audience. When we bump the acid inside the formation, and you will bump it initially with the pH is equal to 0. When it produces back, what will be the pH, the expected pH, when it's completely consumed? Does anyone can give any idea? Just I would like to see like, what's your thoughts about the flow back pH? So you have pH, 7 pH, that's neutral, 14 pH, that's alkaline, just to remind the people the pH numbers. So we start with acidizing with here, with 0 pH. And water, neutral, is a pH of 7, and if it's alkaline, is a pH of 14. So if we start acidizing with a pH here, what's the expected pH of the return fluid will be? Does anyone can guess?
It will be closer to the water, which is 7, like
Okay.
closer. Yeah.
That is perfect. Let's have it as a one answer. answer number one. Does anyone have anything else? Any other? Okay, so to save the time, that will be true answer, but you forget something here. We have a CO2 as a part of the reaction product. And the CO2 will be dissolving in the water that's coming out with the calcium carbonate, make the pH actually slightly less than 7, which will be the actual number between 4 and 5. And that's important part that you like to have for when you do the flow back of the acid. And that's when you are evaluating the acid flow back, you would like to see this pH is coming and to understand how it's been effective. If you have anything in the formation that can pH affecting the corrosion of this one, that's you need to have. But okay. So as we said, like HCl has a lot of advantage. However, it has a lot of disadvantage as well. The first part is the corrosion rate. HCl, as it can react with the formation, it also can react with your pipe system and can corrode your pipe system and the casing and the tubing that you are injecting with. And that can affect the integrity of this tubing. Therefore, we need to use with it a lot of additives like corrosion inhibitor to be sure it will not negatively affecting the integrity of the wellbore. The second part is the reaction rate. HCl is very fast reaction. I wish I can be able to show to you, but if you put a little bit of HCl with a calcium carbonate, the reaction will take seconds, if not less than seconds. Immediately, it will react. And as the acid reacts that fast, it makes it difficult for us to be able to place the acid at a higher concentration at deeper of the formation, because it will react as long as it will see the calcium carbonate. So from design point of view, we need to use some retarding agent, as well as we need to bump it at really high rate to be able to place the acid deeper inside the formation. Yes, the third part is the compatibility with the reservoir and rock. From reservoir fluid, the oil. HCl can do some sludge and asphaltene. If your oil has asphaltene, we need to put some additives there to be sure that it will not cause asphaltene precipitation or cannot cause a sludge. Also, if you have some clay content in your carbonate, especially a light or kaolinite, these clays actually be broken with the HCl. So you need to be sure that is also the amount of clay there can be protected by using some sort of iron control agent or some sort of a clay inhibitor to be sure any sensitive clay inside the formation will not be affected by the HCl and can cause you swelling or fine generation. And the acid is cheap, but as you can see right now, we need to have a lot of additives with the acid that make the package sometimes a little bit expensive. If you have a clay, if you have a sludge, and if you'd like to have a high controlled reactivity or controlled reaction rate. So we need to have a lot of additives with this acid. Any question, or do you like to go?
Just go ahead and, again, if there's any question, I will stop you and ask.
Okay. The second acid is the hydrofluoric acid, HF, and it's the second inorganic acid that we used in the oil feed industry. We mainly use it when HCl cannot be used or HCl cannot be dissolved the material. It's the only acid system that can dissolve silica. That's why we use it mainly for sandstone matrix acidizing, because it's the ability to dissolve the silicate. Usually we combine it with HCl just to be sure that we have enough low pH to eliminate any adding any precipitation and to have a lower pH during the whole treatment. The HF can be used up to 350 Fahrenheit. and from dissolving power is not as a HCl when deal with the carbonate, but can actually dissolve a significant amount of silica. It actually can dissolve up to like 1 gallon of the 12,3 HCl HAF can dissolve up to 0.217 pound of sand. Still high amount, is not as high the HCl with calcium carbonate when we are talking about almost 1.7 for the carbonate case. But still like 0.217 is still high amount of silica to be dissolved. And that is the only acid system that can dissolve silicate. That therefore, when we talk about sandstone acidizing, HAF, it needs to come to your mind because that's the only acid that we can use.
Dr. Goma, I received a question. What if we use only HF and not a mixture of HF plus HCl? What will happen if we use only HF with sandstone?
I'll answer this question in a second. Let me look to the reaction product of the HAF. Here I'm having the ability of the HAF to dissolve. If we reacted with a calcium carbonate formation, the reaction product will have like, if you have HAF plus calcium carbonate, will give you calcium bifluoride plus CO2 plus H2O. Calcium bifluoride is known as a precipitate material. It will precipitate immediately. So if you use HAF immediately and react with the calcium carbonate, you will have a damage and you will end up damaging your well. The second part, when HAF react with the silica, this reaction happens at 2 steps. The first is producing what called flow silic acid, or when it reacts with a dolomite, give you the same acid, the flow-silic acid. And then we have what we call secondary reaction, when the flow-silic acid reacts with the clay, which has a sodium, potassium, or aluminum. And that will be the issue of the second precipitation. You will have a sodium flow-silicate or potassium flow-silicate, and this part is actually will precipitate. Sorry for. The issue of the HAF is the reaction product will have a lot of precipitation. However, this precipitation doesn't happen immediately. It happened at pH when the pH starts 4 to 6. The reason of using the HCl is HCl will not react with any of these. It will not react with the silica, it will not react with the bentonite, it will not react with any sodium clays or potassium clay or aluminum clay. It will stay in integrity and keep the pH all the time 0. If you have a pH of 0, all this precipitate will not happen because this precipitation only happen when the pH reach to 4 to 6. So the importance of HCl, HAF mixture, HCl work to keep the pH low enough to eliminate or prevent any precipitation of the secondary reaction that's happening with HF. I hope this answers your question.
Yes, thank you.
Okay, so going to the other type of the acid, organic acids. And organic acid, again, we have formic, acetic, and citric. And the three is actually, we use them when HCl cannot be used, actually. A lot of time we need some low corrosion rate, and that's happened when we are pumping acid either at a low rate or we're expecting the acid will stay in contact with the pipe for a long time. Then HCl will be a little bit more corrosive to be left inside the tube. Therefore, we are using organic acid in this condition. The advantage is they have a lower corrosion rate. It does not react as much with the tubes, so it does not reduce the integrity of the tube. Also, we can easily inhibit them. We can add slightly of corrosion inhibitor, and we can use them in high temperature. Organic acid being used extensively between 250 Fahrenheit up to 350 Fahrenheit without any issue. Again, if we have a high we use them when we have a high acid by contact time. And that's happened because like sometimes we cannot inject at high rate. So we're pumping really low rate and we have a really deep well. This case, we recommend to use the organic acid. Or the formation have some sort of a clay that we cannot use an HCl. Like in this case, you cannot also pump HCl, so you pump organic acid. Or the tube itself has some metal that will be dissolved by HCl. Like a lot of corrosion, what we called corrosion resistance tubing, which is made of aluminum, magnesium, and chrome. If we pump HCl, you will remove the corrosion protection film and we'll use the integrity of the tube. So in this case, we use the organic acid as an alternate to the HCl. Organic acid can also be used with HCl as what we call iron control agent. It helps to control the iron and to keep it out of the solution, so it will not cause any issue. So what typical additives we use with acid stimulation? Before I go in each one, I would like to highlight acid additives is a very important category, and that's actually the main difference between surface company. So if you like to select between Schlumberger, for example, or Baker Hughes or Halliburton, your selection will be depend on what additives each company can provide to you, the cost and the performance of each chemicals. For example, all the surface company in the market can easily provide you with HCl and HF. It's a commodity product. So you can actually, even some of the production company can actually buy them directly. However, the main distinguish between the surface company is between the package that they can provide to us. The first major additive is the corrosion inhibitor. It is actually one of the main additives and the must additives when we're using acidizing. You will not find any acid formulation without corrosion inhibitor. You must have a corrosion inhibitor with all your additives, and it helps to reduce the corrosion rate. And actually, for each acid, one of the main tests before doing any treatment to do what called corrosion, to check corrosion rate. And it needs to be less than 0.05 pound per feet square. So what you do, you get a piece of the tube that you are pumping your acid in, casing or tubing, and soak it similar to the hour of the treatment. So if you are pumping acid for 6 hours, so you need to soak it in the same acid that you are pumping in 6 hours at similar pressure and temperature to the condition of the wellbore. And check how much weight loss per surface area of the sample that you have. And the value need to be less than 0.05 pound per feet. Do you know, you can see like how much thickness we are losing from the tubing for this amount. Can anyone guess how much thickness of the tubing lost by 0.05 pound per square feet? How much thickness at the end of the treatment? Ahmed, does anyone say anything?
No.
Okay, so it's
But by the way, they can answer because this is a Zoom meeting. So if they have answers, they can speak. So do.
Okay. So 31 micron. Actually, that is the amount. So if you have a corrosion that can reduce the thickness of the tubing more than 31 micrometer, you cannot accept this acid. If it's less than 31, it's acceptable. But higher than this amount is not acceptable. So we're talking about a very small reduction in the thickness that you can accept it. And that's why we need a corrosion inhibitor, to be sure that the acid will not react and reduce any thickness of the tubing that you are pumping the acid in. A second important additive is called corrosion inhibitor intensifier, and we use the intensifier at a temperature greater than 250 Fahrenheit. It helps the corrosion inhibitor to stay effectively at a higher temperature. If you see an intensifier being used at a temperature less than 250 Fahrenheit, it means there is something wrong. It's mainly one of the additives that needed at when the temperature is too high. So it is one of the additives that use it at a higher temperature to be sure to support or to be sure the corrosion inhibitor will work in a more effective way. Iron chelating agent. Iron is one of the things that can actually cause a lot of damage inside the formation. So we'd like to be sure this iron will not be precipitate and be in solution. So we use an additive called iron control agent to keep the iron in solution. Other additives, anti-sludge agent, and it's been used when you have an oil well, and the oil that you have a lot of asphaltene. To be sure this asphaltene will not be precipitate or causing any damage, we typically use an anti-sludge agent. A second part is solvent. A lot of time we mix the acid with solvent to be sure that if we already having asphaltene issue or wax issue, in this case the solvent will be able to dissolve both and will not have any damage coming from the organic deposition, asphaltene or wax. The last thing that to improve the reactivity of the acid, we use retardant agent, and this is help to reduce the reaction rate of HCl by having a polymer or having a surfactant that increase the viscosity of the acid and reduce the corrosion, the reaction rate, allowing the acid to go further inside the formation and be more efficient. So the second part is the acid treatment. What acid treatment we typically do. So we have a different of acid treatments that we typically bump. I will start from pickling the treatment, what's called pickling. Another treatment called soaking, acid breakdown, or matrix oxidizing itself, sandstone or carbonate. And the last one is acid fracturing. So we will go one by one and see what does each treatment do and what's the typical acid that we use for each treatment. First one is called pickling treatment, and usually we do this before any acid job. The process is pretty simple. We are circulating usually a low acid strength between 3 to 5 weight % HCl. And the idea here, we try to remove any iron or any rust in the pipe. So even if the pipe is new, usually you will see some rust inside the pipe. This rust, if you bump your acid and the acid will go through the formation, all this rust will go inside the formation and cause the damage. Therefore, we try to circulate an acid like 3 to 5 weight % HCl to try to make it, to bring it like as a new, or remove all the rust, something to the shape. And all this rust will come out and will not go inside the formation. So simply you circulate the acid inside the well bore. If you have this treatment called pickling treatment, usually the acid concentration between 3 to 5 weight %. And mainly you have two types of additives there. Corrosion inhibitor as a must additives with any acid treatment. And we are talking about removing rust, which is mainly iron oxide. So we need to have some sort of iron control agent that's also go with it. So usually it's a pretty simple acid, 3 to 5% HCl with some corrosion inhibitor and some iron control agent. A second treatment, it has a different name. Some people call soaking, some people call agitating, some people call acid washing. And the idea here, or the process here, is pretty simple. We like to put some acid inside the well bore and we soak it for some time to remove any scale inside the tubing. And I'm not sure if you can see the picture or not. Can you see this one? This is the amount of scale that's been deposited with time. So as you are producing calcium carbonate, one of the major scale that will stuck in the tubes and build with time. And you can see it's pretty thickness and can actually reduce the effective diameter of the tubing, reducing your rate. So what you need to inject some acid, soak it there, leave it there for a certain time, allow it to dissolve this material and to restore your initial diameter. You will be able to remove all the scale. Also, you'll be able to remove or open the perforation. Some of the scale also will be stayed in the perforation and plug it. So you will be able to clean the perforation. And if any scale also in the formation phase, it will be removed. Usually, the main additives that go with this acid is a corrosion inhibitor as a must additives. And depending where you are, if you are mainly soaking the acid inside the tubing, you will keep the corrosion inhibitor only. However, if you are expecting this acid will leak inside the formation, in this case, you need to add additional additives depending on the formation. So you are having a sludge issue, you will have anti-sludge agent. If you need some solvent, you will add some solvent. If you need iron control agent, you will add iron control agent, depending on what the formation that you will have. Other treatment called acid breakdown job. And in this case, you are mainly try to affect the perforation. Usually when you have a new well and you are perforated with a perforated gun, there will always be a debris inside the perforation tunnel. So what you would like to do, you will pump some acid, try to remove this debris and increase the effective diameter of the perforation. We call it acid breakdown job, or sometimes they call it just a breakdown job. Or sometimes the people call it acid spread head, which you bump it in front of the frac, try to clean the perforation. Typical additives that use, as usual, corrosion inhibitor. We are here targeting an perforation, so definitely the acid will go inside the formation. Therefore, you need to be sure that you will have the formation compatibility additives with you. So whatever additives you need to be sure there is no damage to the formation, you need to add it there. Usually you are not targeting one perforation, you are targeting group of perforation, and therefore you need some sort of diverter agent, some sort of, like if you are treating a certain part of perforation, you need to be sure that you're treating the other parts. You need to divert from the one that cleaned first to the one that will cleaned later. After that, we can move on to the major acid treatment. Here, the first major one is the sandstone acidizing. And as we just said earlier of the presentation, the main acid that's been used to dissolve in sandstone is the HF acid system. And as we are talking about sandstone acidizing, so we're still talking about matrix acidizing. So we are injecting the acid at a pressure or at a rate less than the fracture pressure. And you can see here, I have like a simple cartoon that show the acid as it moving, and you will have your pore structure or your formation pores. What's happening? The acid will react in the face of the pore and dissolve this part. In sandstone, as you are dissolving this part, you are actually improving the porosity and improving the permeability. You are not creating wormhole as we will see in carbonate, but you are just enhancing a little bit this one by dissolving the contact between the acid and the mineral phase or the formation phase. The best way to inject sandstone acidizing, usually we do it in a 3-step. The first step, we inject HCl only. And the idea here is just to remove any carbonate. We know when HF react with the calcium carbonate, is producing calcium bifluoride, and calcium bifluoride will precipitate immediately. Therefore, we would like to pump HCl first to completely dissolve the carbonate. So when the HF coming later, we'll not see carbonate. We'll see only silica that will be dissolved by the HF. So initially, we pump HCl just to dissolve any carbonate that if it existed when the HF see it, it can cause damage. Then we go with the main acid, which is HCl-HF treatment. And the acid will work toward the silica and dissolve the silica. Behind it, at the later stage, we'll do overflush with HCl. And the idea here is to keep the pH as low as possible. So you cannot reach to the pH 4 to 5, and you don't have any precipitate. When we talk about the HCl-HF, we have different ratios that we can use. Sometimes we don't need to have a really high strength acid. We need some called diluted mud acid or some sort of a low strength of the acid. In this case, the HCl will be a concentration less than 7%, and the HF will be less than 1.5%. However, the typically what we call the regular mud acid or regular concentration, usually between 7.5 and 12% HCl, or 1.5 and to 3% HF. And usually it's actually 12 HCl and 3 HF. That's a typical and the most used one. However, in some concentration, we really need the high concentration of HF. In this case, we'll go with the HCl concentration to a higher value, like almost 16% or 6% HF. But we don't use it that often. We use it only if we need really to dissolve a lot of silica near wellbore area. But typical one is the regular mud, which is 12-3. That's a typical one that we typically use in the field. A second point is the carbonate acidizing. And in this one is a little bit different than the sandstone acidizing. In this case, we are actually creating a wormhole. The reason that we are creating the wormhole because the acid that we are using will have a much higher dissolving power. If you just remember, like HCl who interact with carbonate, 1 gallon will dissolve 1.7 pound. So, and will dissolve it that fast. Therefore, when it reacts, it actually will create the channels inside the formation because of the dissolving power is too high. These channels, we call it wormholes. And depending on how fast we inject the acid, the shape of the wormhole will be actually a change. So I have here the different shape of the wormhole as a function of the rate. So that's what we call dominant wormhole when it's really thick. Let me have it in the second picture. That would be much more easier to understand. So I'm going here from low rate to really high rate. And that will be the shape of the wormhole as we are going. So if you are pumping the acid at a really low rate, you will not have enough acid to go inside the formation. So whatever acid will do, it will react mainly with the surface of the core, and you will dissolve the surface of the core. That's what we called at the beginning phase dissolution. Increasing the rate a little bit will allow the acid to go a little bit deeper, but still react more at the surface than deeper. That is will give us like what we call like conical shape, like a cone shape. However, if you start increasing the acid rate more and more, you start getting what we call dominant wormhole, when it's a long pipe inside the formation. So as you are injecting here with a high rate, you can see the wormhole is going pretty deep. Usually you can see still inlet is a little bit bigger than deeper inside the frame, until you reach what we called dominant wormhole or optimum wormhole. The optimum wormhole usually you will see almost has a constant diameter through the section, and it will take the minimum amount of the acid to reach to the deeper area. when you increase the rate furthermore than the dominant wormhole or the optimum wormhole, you will start seeing a branching effect. As you are bumping, the acid will move in this direction, deeper direction, as well as it will leak at the side, create a lot of branching. So depending on the rate, the branching intensity will increase. The higher rate, you will have a more higher branching out of the side. Usually at our design, we like to design targeting this one. So in the lab, we get a core, actual core from the field, and we get several cores and we run different rates. And we see which rate is give us the optimum wormhole, and we try to design our injection rate in the field close to this optimum rate to be able to get an optimum wormhole diameter in the field. That will help us to reduce the minimum of the acid that we'll use and get the maximum benefit of the acid in the field. The last treatment that I will try to cover is the acid fracturing. And here we are bumping the acid at higher pressure, more than fracture pressure. So what will be happen? We will create an actual frac. So if you bump it, you will see like I have here, like this is a sort of the frac that been created with acid. You are not anymore bumping acid in another direction. What's happening as soon as you create the frac, all the acid will go toward the fracture. What the acid will do, the acid will start react with the fracture's face, create uneven pattern. So when you close, the uneven pattern will create a permeability that is big enough to have the flow through it. So let me have it this one. So what's happened? You have here a fracture face. And you have an acid that create actually a long pore structure through it. So when the two pieces of the frac is closed, you can see you have a still big area that the acid will be flow. And that is what we call good etching or good channel development. However, sometimes you did not create this big one. You create actually a small one that is insufficient, and that is mean that you didn't bump enough acid or you did not distribute it well. That is happening by creating a small area. With time, it will be closed as you are closing, having a higher closure pressure on the side.
Dr. Gom'a, I received a second question. Someone asking how are inhibitors different from retarder?
Inhibitors is used to well, I believe you are talking about corrosion inhibitor and retardant. Inhibitor
Yes.
is actually creating a layer in the tubing. Okay, let me have it as a go back a little bit here. Okay, maybe I will delete this one. Okay. So corrosion inhibitor, if you have your tubing here, usually corrosion inhibitor create a layer at the tube, a protection layer on the tube. This layer eliminates the acid to diffuse on the surface of the tube and protect it. That is a corrosion inhibitor, how it do exactly. Retardant is actually increase the viscosity of the acid itself, make it a little bit more viscous, so the movement of the acid itself will be much less. So corrosion inhibitor, by definition, just absorb it. It works only in the tubes, and what it does, it just build a protective layer film on the tube surface. However, retardant is work actually in the viscosity parameter. It makes the viscosity of the acid going from 1 centipoise to several hundred of centipoise. So it has a higher viscosity, the acid will not move that easy, and it will not react that easy as well. Okay. Any other question?
No, you can go ahead.
Okay. The other side of the acid fracturing, if you bump too much acid and actually you etch all the surface. And if you over etching it, what will be happened? You will end again with similar condition like insufficient etching. When it's closed, you're creating too many opening area that when the two pieces of the frac is closing to each other, it will end us with a very poor conductivity, and the amount of the conductivity that you will have is much less. So in the acid fracture, you would like to be able to be sure that you will have enough acid distribution to create a good etching without bumping less acid to have a very minimum etching, or bumping too much acid that can actually dissolve everything. And when you close, you will not have this ununiform pattern good. So the best way to do the acid fracturing, we do it in a 3 different steps. The first one, we bump across linked bed and to create the frac. So first thing you create the frac, and the size of the bed is depending on how the geometry of the frac you have. If you like to have a larger frac, in this case you bump across linked bed a big one. If you just need to have a small frac, you will bump a small bed size. So the bed size is definitely give you the fracture geometry that you are targeting. Then after you create the frac, you bump your acid system, and usually use 15 to 20% HCl. If the temperature is too high, like above 250 to 300 Fahrenheit, in this case, sometimes we use acetic and formic acid as an acid for the acid fraction. However, majority of the time is just between 15 to 20% to 28% HCl. Then after the HCl, you go with a flush. And the idea here to be sure that you don't leave any acid inside the tubing, just all the acid being bumped to the formation. So if you do this, that is a typical step, 3 steps you do for acid fracturing. The final part of the presentation is acid placement, which is happening. How can you be able to be distributed the acid through the wellbore? So acid is known as a reactive fluid, and as it's bumping inside the formation, it will increase the permeability of the formation. So imagine if I'm having a wellbore like I have in this cartoon, and I'm actually bumping acid. As like any fluid, it will go first to the high permeability formation. So imagine I'm having here 3 types of layer, like really high permeability, 1 medium permeability, and the top layer is a low permeability. So I will say this is high, this is medium, and this is low permeability. When you pump the acid, what will be happen? Usually acid will go initially to the area with the high permeability, and as the acid go in this high permeability, it will enhance the porosity and will make it a higher permeability. So what will be happening, acid will keep going in this zone. It will not go to the medium or the low permeability, because simply, like any water inject, would like to go to the least resistance flow. So with this concept, acid will not touch the medium permeability or the low permeability zone. And you will end only with stimulating 1 zone out of 3. And if you have 4 or 5 or 6, that will be happening. It ends up with simulating 1 or 2 out of multiple zones that you are targeting. Therefore, we need to have what we call acid diversion technique, or another technique that can help you to have this type of diversion. So I will pause this one right now. So the placement technique that we have either mechanical or chemical technique. Mechanical is example, we have cold tubing, Barker, bridge plug, and ball sealers. Or chemical techniques, we have foamed acid, emulsified acid, gelled acid, and in situ gelled acid. Just to go one by one like mechanical, we have cold tubing. And in this case, we're actually using a cold tubing to spot the acid at each location. So in this case, you are guaranteed that your each zone take the acid. So you are bumping using the cold tubing the acid at each zone. Another one, use Bakers. So simulate a zone, then put a Baker, simulate another zone, then put another Baker, simulate a third zone, and you put a certain Baker. So you use a Baker to isolate the zone that you are trying to inject. So inject, and then close, go to another area, inject, and then close. So using a Baker, multiple Bakers to be able to distribute the acid through the whole zone. Similar to the Baker is a bridge plugging. The same. Simulate a certain zone and then add a plug and move on. Simulate the zone that you like to have and then add another plug. And at the end of the treatment, drill all these plugs that you are having. Final mechanical one is actually ball sealers. In this case, if the acid will go in the hypermobility zone, bump some sort of a ball material that will sit in the perforation and close this perforation. So in this case, you are not having buckers or having cold tubing. You can bump something from the surface that can actually plug each perforation. We call it ball sealers. This mechanical method is actually is the best method to be sure that we have a good distribution. It's all of it. You can be sure that when you are using mechanical, you are pretty sure that you have a good placement, and you are 100% sure the acid been evenly distributed or distributed in the way that you like to have. However, it usually needs cement, certain type of completion. You need to have casing and cemented most of the times. If you have an open hole completion, a lot of this mechanical method does not work pretty good. It controls the fluid only inside the wellbore. When it goes to the formation, you don't have any control. It may actually bypass behind the casing, and you cannot be sure that the acid will actually will go to the zone, the target zone. It may actually go to another zone. Third and most important, it's expensive. It's pretty expensive to use. Imagine using for each zone that you are targeting a bridge plug or a Baker. That's pretty expensive. And then after that, you need a drilling rig or workover rig to drill all these plugs and remove it after the treatment. It also make it a little bit costly. So mechanical method is a good working. It's a good isolation. However, it had a lot of disadvantage, and the main one will be the expensive, the cost. The cost will be extremely high. Again, we have a ball sealers, which is still a part of the mechanical. It works only if you have a perforated well. You need to have a perforated casing and cemented. Also, it needs a high bumping rate. If you are bumping at a low rate, it will not work. And designing how many balls you need to run is a little bit like critical. And not all the time is being designed right. And you may actually plug a formation that you need actually to treat it. So still a little bit tough to deal. Therefore, we like to use a chemical method for acid placement. First, chemical method will work on all completion type. So it doesn't limit you to any completion. The way that all this chemical method is working the viscosity. So what you do is just increase the viscosity of the reservoir fluid. You increase the viscosity of the acid more than any fluid in the reservoir. So it help you having good sweep efficiency and a good distribution. All this chemical transform the fluid to be a non-Newtonian shear-thinning behavior. So when you bump it at higher rate, it will have a low viscosity, but as it's going inside the formation, it will have a really high viscosity. It helps you control the fluid inside the formation and also give you a good retardation. The wormholing will be much efficient using this chemical method. So mainly we have a tool for the chemical method. The most used two things right now is in situ gel acid based on polymer and based on surfactant. And the polymer one is not used as well, but however, the most recent one is a surfactant and been used extensively in the field currently. Some people call them self-diverting acid or viscosity control acid, but it's the same name or the same behavior. So the idea here is working with the pH. At a low pH, the acid will have a low viscosity, and when the pH is reach around 2, actually the polymer will be cross-linked and initiated a really high viscosity. And at that region, you will have a really high diversion power. As soon as the pH go to above 4, it will be completely broken and you will not have any damage or any concern during the flowback. And the way that it works in the field, you are bumping the acid. Again, it will go through the hypermobility formation. However, inside the hypermobility formation, when the pH increases to 2, the gel will be formed using a really high viscosity plug. It will plug the hypermobility zone, making the next acid to go to the lower permeability. And as it's going through the lower permeability, it will start from pH 0. As it reacts, the pH will increase to around, again, 2. The fluid viscosity will increase, plugging the medium, forcing the acid to go to the lower permeability. In this case, using just one fluid, you will be able to place the acid through the whole job. And at the end of the treatment, when the pH increased to around 4, all this high viscosity will be completely broken and flow back, and you treated the whole section without any issues. Actually, that was my last slide today. So please let me know if you have any questions.
Guys, please, if you have any question, you can go ahead and ask. Any question before we finish? Okay, Dr. Ahmed, thank you very much for the informative session, and for sure we wish to have you again in the future. Thank you.